We did it.
Here we are.
Live.
Boy, small crowd today.
Yeah, it really is. This is every now and then we run into this, and this is when you're truly tested. The maximum test is when it's just me and one person. That's when.
Have you done that before?
Oh yeah.
Wow.
Yeah. Morgan, there's been several episodes where it was just Morgan Sternberg and me going through all the stories, and it's funny because people will, after the fact, they'll go, "That was great." Like, it can be anywhere between 2 people and 7 people. Anywhere in between is perfectly fine.
Yeah,
especially with a rock star like Morgan.
Well, that's exactly it. Yeah,
professionals, you know.
Yeah, exactly. Morgan can just go and can absolutely fill whatever amount of space is required. But it's the same thing. Like Alex, you know, I've interviewed both of you guys.
Yeah,
and
that's true.
You know, we go for an hour, and now it's about the stuff that you're specifically working on and have a tremendous amount of expertise in. But
right.
But it's that. Well, Pamela's like, you know, here in spirit. Just a voice that haunts us from beyond.
Just in our ears.
Yeah, just in our. Well, can the audience hear her too? I don't know. I never know. Yeah, you know.
Now they can.
If Pamela wants. There you go. If Pamela wants to jump in and feels the need as she's engineering this episode to jump in and contribute, she can, especially since we're shorthanded. But the magic that Pamela and I figured out, I think, is that Pamela is has a background in like stand-up or like improv, and the trick with the whole improv is it's this yes and.
Yes.
So if you listen to us, and you know, whenever you do a podcast, you just yes and what the other person is saying every time. And
That's what the McElroy brothers say.
Yeah. Yeah. And then it just flows. It just flows like butter, because they'll say something and then you'll just yes and you might have just like literally be completely disagreeing with what they just said. It doesn't matter, because you're like, yeah, and like this and that and that. And then you can carry the conversation for the entire time for as long as is required. So yeah, I feel like, and Pamela led with that. Like, was that like an improv thing, Pamela? I'm not sure where that came from.
It was a combination of not so much improv as being on debate team and having to back up the other people on my team. And when you're trying to work with a group to communicate an idea, you can't but the person that you're with, because suddenly you've invalidated everything they've said. So you have to figure out how to yes and it, even when they're totally full of whatever.
And it's like you feel like you just talk, and you're like, for me anyway, like when we're doing Astronomy Cast, I'll feel like I'll say a bunch of stuff and I'll go, you know what, that's enough talking for me now, and I'll just stop. And then Pamela will just have to pick up, even though she doesn't want to interrupt. I'm not leading her into anything. I'm just dropping the conversation at that moment. And now she just has to pick up the ball and just, you know, the baton, and just keep running with it, and then back to me. There's almost like an instinctual feeling like, okay, I've said enough words in a row that it's time for the other person to start talking, whether or not it's an actual gap in the conversation. So anyway,
it's a little like jazz, you know. You got to just keep it going. Somebody, you know, going to play for a while, and then or I'm always using this like volleyball analogy. You know, you have it the ball on your side, maybe one touch, maybe two, maybe three. But then you have to toss it over to the other side. You know.
Yeah.
You want to just like keep the ball in the air. Everyone makes fun of me for that analogy, but
you can feel when the person doesn't trust you is because they don't stop talking.
Yes.
Yeah, if they're not giving you the space.
Yeah, and then you know, okay, they think that I'm gonna do a bad job of whatever it is that I'm gonna say. And so that's how you can just get a sense of it. And vice versa, is you can feel yourself going, oh, they're not ready. They're not ready. They're not ready to grab, to take over the handoff. And you've just got to let them fly free and just let them go, which is, my job as the
Painful.
moderator for this show. Well, it can be, but, my job as the moderator is to push these baby birds out of the nest no matter what. So, yeah. All right, let's do it. Let's get this thing started. You guys all ready?
Sure, ready. Let's do it.
Go, no, go. Alex.
Where'd it go?
Go, no, go, Moya.
Moya, sit backwards. You cut off your lips. There you go. Much better. Thank you.
Okay.
Hello.
All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, May 4th, 2022. May the 4th be with you. This week, we're going to be talking about cosmic rays as earthquake detection, machine learning for exoplanets, rare galaxies forming stars, solar flares, Event Horizon Telescope, James Webb, Rocket Lab, Starliner, and anything else that comes up in this news-focused episode of the Weekly Space Hangout. Joining me this week, I've got Dr. Alex Tichy. Alex.
How you doing, Fraser? Good to be here.
How's Taiwan?
Taiwan is great. It's beautiful weather.
Oh,
always.
That would be
Except
nice.
when it's rainy. It's very rainy.
Or droughty. I hear it can get droughty there.
Down in the south, we were having droughts last year. Yeah. But in Taipei, it's always raining. It's like twice as much annual rainfall as New York City, actually. I didn't know that until I came here. But it's
twice as much rainfall as New York City.
Yeah, it's pretty rainy. Not like New York is like known for rain, but anyway, it's very rainy in Taipei. Actually.
Now I want to see how Vancouver, how we do compared to you.
Yeah, that's a good question.
Yeah.
I don't.
Yeah.
We might beat you. It's pretty rainy.
Yeah, but warmer. Awesome. All right, we got Dr. Moya McTeer. Hey, Moya.
Hello. So happy to be here. It is not raining in New York right now.
Right. So there you go. We could literally run that test right now between Alex, Moya, and me. Who gets more rain?
Oh, we could.
Yeah.
Is it raining there right now, Alex?
No, actually, it's a beautiful day today. I don't know. I mean,
it's raining here right now.
Vancouver's
okay. Fraser wins.
Yeah. And the loses. All right. Before we get into this week's news, I want to give a huge shout out to our good friends of the Weekly Space Hangout crew. Our friends, our fans, our executive producers. Join this incredible community. Go to wshcrew.space and they will hook you up with all the information that you need to become an executive producer of the Weekly Space Hangout. All right. Let's get into this week's news. Alex, I choose you. Let's talk about cosmic rays as a warning system for earthquakes. I've never even heard anything about this. I'm looking forward to learning something new.
Yeah, so this was sort of wild. I was going through, looking at the news of the past week. There was nothing that was really speaking to me directly. So when I found myself in this situation, I go through the archive, get the papers that have come out. Maybe nobody's really written an article about it at all. And I spotted this thing, correlation between cosmic rays and earthquake events. And so this immediately, sort of sent off warning bells in my head, like, what's going on here? Cosmic rays causing earthquakes, that sounds nuts. I got to look at this paper. Of course, that's not what they said at all. They didn't say causing earthquake events. They said correlation, right? As we well know, correlation is not causation. So I start looking into this. This paper is actually going to come out in Science. Someone's putting a fair amount of stock in this anyway. So what's going on here? We're interested, obviously, in earthquake prediction, right? Earthquakes are notoriously difficult to predict. They're happening all around the world all the time. Big ones, mostly small ones. We have them in Taiwan all the time, and I've only felt a couple of them, but we get alerts on our phones, once every couple of weeks. Earthquakes are happening all over the world all the time. So we want to predict them, particularly when they're these big ones that can obviously be very destructive. So what can we do? Let's think outside of the box. The idea here is, fairly straightforward. Earthquakes happening inside the Earth. There's churning. There's all kind of stuff going on inside the Earth. So could it be that the movements inside the Earth, particularly in the core of the Earth, we have this iron core, it's churning away, produces this dynamo effect, produces the magnetosphere of the Earth. So we say, is there a connection here between what's going on inside the Earth and what we can see in the magnetosphere? And could that be sort of an early warning sign of earthquakes? So where the cosmic rays come in is that we have these cosmic rays streaming to us from all across the universe. They hit the magnetosphere, they hit our atmosphere, they produce these air showers. And so the idea is that if you start to see changes going on inside the Earth that imprint themselves on the magnetosphere, then you might be able to trace that through changes in the cosmic rays, and then that could be an early warning sort of method. Now, the idea kind of came out of this large 8.8 magnitude earthquake in Chile that happened a few years ago, and that they had noticed about 2 or so weeks before this event that there was this anomaly in the cosmic ray rate. And so they said, this maybe not so crazy. Let's take a look at this. Now, skip ahead a little bit to say that, what you're really hoping for is that you can do this kind of localization where you would say, all right, we're seeing something weird happening above Chile or Sumatra or wherever it happens to be. And 2 weeks later, we can expect an earthquake here and we get ourselves ready.
Is that far in advance?
Well, so this is what they're trying to do. They're looking for these correlations, and you can do this kind of, looking at the changes in the rate of the cosmic rays, looking at the earthquakes. Now, what I was about to say is that they can't do this localization, not yet anyway. So what they do instead in this paper is that they find a correlation between the cosmic rays and a global sort of sum of how how many earthquakes or the size of these earthquakes. You add them all up globally, and you can sort of track these changes. And there's about a 2-week lag there. Well, that's what they're claiming anyway. Now that doesn't sound incredibly useful. It's like, okay, well, somewhere in the world there's going to be more earthquakes. Everybody get ready. It's not necessarily going to be super useful, but of course, in science, it's just one step at a time. We find this sort of new phenomenon, and maybe there are other things. Now, I'm, frankly, a little skeptical. I don't want to talk about this paper as though, this is definitely something that they found. It is in science. It's not in nature. The joke that astronomers at least have is that if it's in nature, it's probably wrong. I don't know if we have the same thing about science. Science, this is a very reputable journal, obviously. And so, like I say, it's a global phenomenon. They do see this thing. They actually start to talk about the solar cycle at some point in this paper, and they're sort of tracking these differences. Now, this makes a fair amount of sense that something going on in the sun could impact us here on Earth. I frankly didn't really follow that angle of it.
But would it be the same thing? Like the same thing that essentially the level, because I know like the magnetosphere and even the upper levels of the atmosphere will puff up or go down depending on the solar activity.
Right.
And so you've got this solar activity that's coming through. And so I guess I'm envisioning you've got this changes in the magnetic field lines are maybe changing the size of the magnetosphere. It's puffing it out, bringing it down, contorting it in these weird shapes. And then that's interacting with these cosmic rays that are increasing or decreasing in just the total quantity, depending on the thickness and strength of the magnetosphere at different areas.
Right,
It's a fascinating idea, and I can definitely see, if you could go and set up a Cherenkov radiation telescope on all of the hot spots where earthquakes could happen, and then wait for cosmic rays to come zipping through the atmosphere, then maybe you could get to a point where you could have your 1 week's notice that something big is coming.
Yeah, it would be super useful, obviously. I mean, earthquakes, like I say, they happen all the time. And I think we've, gotten pretty good at understanding at least certain aspects, but the prediction part of it is something that we still, there's still a long way to go. We'd like to, they're just totally random. You wake up, it's 2 a.m, all of a sudden, I get about a 5 or 10 second head start, maybe. My phone starts going off. We get these alerts on our phone, and 5-10 seconds later, the whole room is shaking.
We had apparently 400 in the last couple of weeks here on Vancouver Island.
Wow.
Yeah, I didn't feel any of them, so none of them were that significant. But it's the same as you, Alex. We feel them all the time, and it's a little unnerving.
Yeah, I don't think I could live like that with regular earthquakes.
You have hurricanes.
Happening.
We have no hurricanes here.
Okay.
Alex, you've got both.
Yeah, we do get the typhoons. Yeah, that's true. Yeah, but typhoons, you can see them coming, several days in advance.
I am 100 kilometers away from the equivalent of San Andreas Fault, like the the Cascade subduction zone. It's a nasty one, and there are fish skeletons thousands of feet up the side of mountains from bad tidal waves in the past. Yeah.
Now, I remember there was this
City.
article that went around many years ago about, I think Seattle, right? That was you're ready for this big one. The big top was going to blow. Would Vancouver be affected by that?
Oh yeah, yeah. If Rainier goes off, we wouldn't be in the pyroclastic flow, but we would definitely be in the. We heard St. Helens go off. It was this loud bang that went off. It sounded like an explosion just close by. Wow. And then on the radio you learned that was Mount St. Helens, and then we got ash falling down on our cars, on everything from the ash cloud from St. Helens. I know this has nothing to do with what we're talking about, but, but that's fine.
Yeah,
tectonic, seismic events. Yeah.
When you first started talking about the story, I did not expect the cosmic rays to be detected in the atmosphere before they were used in this correlation, because cosmic rays pass through the Earth, right?
Yeah, I think so. Yeah. Right.
Yeah, so I expected that it would be, detecting the neutrinos after they've passed through and seeing any distortions in the internal activity that way. But I guess not.
Well, so I don't know exactly where they do the detection, frankly. They have these detectors. The detectors are clearly on the ground, but it's just these secondary cosmic rays, right? So so
I think that's Cherenkov radiation, right?
Yeah, right. So it comes out all kinds of different sort of particle, striking something, and then there's this sort of chain reaction of events that come down, and then they're detecting those particles. I'm totally out of my element.
This is one of Pamela's absolutely favorite pieces of science, and I don't know if Pamela. Mention it.
So the Cascadia fault line or the cosmic.
No. Well, I know you love a deadly volcano earthquake, but no, the Cherenkov radiation, the fact that they're moving at relativistic speeds, and thanks to time dilation, they decay.
Yeah, so just the fact that there's so many particles that we detect at the surface of the planet that shouldn't live that long, but they're moving so fast. I love relativity. I also love the Cascadia fault line from a distance.
Yeah. So these particles, these cosmic rays, as they hit the atmosphere, they get broken up into a bunch of subparticles. The subparticles should decay in the time it takes to go from where they hit the atmosphere to the ground, but because of time dilation, because they're going at 99 point whatever the speed of light, they experience a different amount of time for them than we experience on the ground, and so that they live longer than they should, long enough for these Cherenkov radiation telescopes to be able to detect them. It's a mind-bending thought, and we wouldn't be able to detect them if it wasn't for time dilation, for relativity. So it's incredible.
Super cool. I love those like real world examples of time dilation, special general when we can actually see it, like GPS. How if we were taking it, relativity into account, GPS would be miles off. It just wouldn't work because of these. It's just tiny little changes, but it's really happening. It blows my mind off every time.
All right, Moya, let's talk about rare galaxies forming stars.
Yes, let's do it. So the story of galactic evolution that I remember learning in school was that you have these separate galaxies, probably spirals, that are attracted to each other through gravity. They collide, and their collisions trigger really strong bursts of star formation, and then gas gets flung out of the system, maybe because of an active galactic nucleus in the center, or maybe because of feedback from stellar winds. But the gas leaves, leaving behind a so-called red and dead elliptical galaxy. And we've seen galaxies at all of these different stages. We've seen the individual spirals, we've seen the rapid star-forming galaxies, and we've seen red and dead ellipticals. But we haven't really seen this transition phase in between. But new research from the Astrophysical Journal revealed this mysterious trait about one of these intervening stages called post-starburst galaxies. These are galaxies that have already undergone their rapid star formation process, and they aren't forming stars anymore. ALMA observations of 6 post-starburst galaxies, or PSBs, show that, contrary to what we've thought about these galaxies so far, that they actually aren't gas deficient. They haven't had their gas stripped away from them or pushed out from the center, and instead they have a lot of gas concentrated in their centers, but they're still not forming stars.
Is the
they're
gas
actually
too hot?
Yeah, that's one of the potential causes. They studied continuum emission and carbon monoxide emission lines from the 6 PSBs with ALMA data, the Atacama Large Submillimeter Array, or millimeter/submillimeter array. They were using that to figure out how much gas there is in these galaxies, where the gas is, and how it's moving. So the kinematic data of this gas structure. They found that they're only 10% as efficient at forming stars as pre-collision galaxies with similar gas densities. So what is going on there? When they look at the kinematic information, they found that the interstellar medium, the space between stars in these galaxies, is warm and turbulent. And so the churning of the gas in these galaxies inhibits star formation. But they need to do more research to figure out exactly what's causing this kind of turbulence and how it's impacting the star formation rate. But it seems like these galaxies are too warm and too mixy to make stars.
So the galaxy has gone through some kind of interaction. It's gobbled up some neighbor. It's gone through this process of furious star formation, but instead of using up all the gas, like all the ultraviolet radiation coming off the stars, all of this star formation is actually just heated up all the leftover material, and now it can't collapse into more stars, but it's still there. And so now you have to wait to cool down before it can turn into stars again.
But it might not ever cool down.
Yeah.
Or it might get to the point where the gas is flung out of the galaxy, so there's no gas left to form stars.
Huh. There's got to be some kind of analogy here. Like, I'm sure that's waiting for the press officer to figure this out, that they live fast and die young, or I don't know.
Well, these are the major mergers. So these are galaxy collisions between galaxies that are of similar size, as opposed to minor mergers where one galaxy is so much bigger than the other one. And I love marriage as a metaphor for major mergers of galaxies, because it's really hard to take two separate lives and bring them together. It's messy. Some stuff gets thrown away. Some new stuff gets created. So yeah, that's the analogy I go with.
That's us in Andromeda. And then you end up with like a leftover spherical galaxy as opposed to a nice grand spiral.
Yeah, exactly.
And one of the galaxies is like, can we throw away that KISS poster already? You've had it since college.
Yeah, that's awesome. All right, so I'm going to talk about the James Webb. Finally, comparison of James Webb, and hopefully we'll be able to get this image. So, people have been asking me, like, what is the first picture that we're going to see from James Webb? And I was theorizing that what we would get is some kind of comparison. We would see an image of something that we had already seen with other infrared telescopes, just so we could get a sense of how the James Webb is better compared to previous observatories. I was expecting this would happen in a couple of months from now when they do the final science images, but they're still in the initial testing out phase, focus phase. And so, as you know, all of the various instruments on board Webb, the primary mirror, the secondary mirror, are all essentially within their operating temperatures, all of the instruments. And the one that's important is MIRI, which is the cooled instrument on board Webb. It's down to 7 Kelvin and is now able to capture these really cool images in every sense of the word of the universe. And what was amazing is, so they did these first images just to to test the focus, and someone on Twitter went and dug up that exact same region that Webb had captured with Miri, and then found that image in WISE and found that image in Spitzer. And it's a region in the Magellanic Cloud. I think it's the Large Magellanic Cloud. And so on the left, and I apologize to people listening to this in on the podcast, but on the left, you see the image on WISE, and that's at 4.6 micrometers as a wavelength. And then you've got Spitzer at 8.6. And so in WISE, it's just these great big blurry blob stars. And in Spitzer, they're a little better, and you can start to see some of the nebulosity. And then in Webb at 7.7 micrometers, it is perfect. It is these tack sharp stars, this faint nebulosity. It couldn't be clearer just to see the comparison from WISE to Spitzer to Webb. It's stunning. And again, this is not them doing actual science data. This is not them doing a deep field. This is them just making sure that it's focus, that Webb is in focus. Oh, and by the way, here's a picture, tack sharp nebulosity that we've never seen with this level of clarity, with a bunch of galaxies in the background. Just a random deep field, whenever it wants. It's crazy. Yeah.
Yeah, it's really dazzling. I mean, you can't even see that nebula at all in the WISE imaging, especially. You see little hints of it in Spitzer. And you can just multiply this by, I don't know, 10,000 times how much we're going to see across the sky, all of these sort of structures that we've never seen before. I can't wait to see what comes out from JWST. It's really going to be unbelievable.
Yeah. And I think this is the mic drop. Like, we've been a month early, because, and it was Andres Gaspar, I think, found it and lined this all up perfectly and found those comparisons. And, a lot of people have been asking, like, when will we see it versus Hubble? But Hubble does not operate in the same wavelengths, does not have, it's not a valid comparison. And so what you would see in the visible light or an ultraviolet from Hubble or even near infrared just doesn't compare to mid-infrared as what you would see with James Webb. And it just shows you, it's just this wonderful just sneak preview of what we're in for with Webb. I love it. So excited.
Incredible.
Yeah. This is just one of the instruments aboard, the mid-infrared one. What are some of the others?
Oh, I forget the name. There's like the picture where they released the Miri image, they released a full set of all of the images and all the instruments, and they were roughly in the same region, and they took kind of versions of that area with the different instruments, as you got a chance to see what it was going to look like. The names of all the, hold on, let me get them, because there's not a lot.
Yeah, we've got near spec, near cam,
there you go.
Near-is, I guess. I don't know. Yeah, and the fine guidance sensor. It sounds like it. That's just probably a fine guidance sensor, but the imaging looks pretty good all the same.
Yeah, and so Miri is the only one. The mid-infrared instrument is the one that has to be cooled down, because all the other ones are near infrared.
Mm-hmm.
And so they're starting to overlap over what Hubble does, but Miri is the one that is cooler, that is seeing stuff from 7 Kelvin as opposed to, I think, what was it? The primary mirror is like 60 Kelvin and the secondary mirror is 40 Kelvin. Maybe I'm getting that a little off, but in the dozens of Kelvin, but Miri is down to 7 Kelvin. So yeah, nice. Absolutely incredible.
We're going to get some great science with this. It's going to be awesome.
Oh yeah. Well, there's one thing I was sort of researching, is that with Webb, we'll be able to see what Hubble could see when it had a gravitational lens. So galaxies that are just a few 100 million years after the Big Bang, Webb will be able to see the stuff directly anywhere it wants. It doesn't need to wait for a gravitational lens to be able to see it. But if it does get a gravitational lens, then it gets a 10,000 boost in its capability, and it can see population 3 stars through gravitational lenses. So in addition to it being able to see any galaxy it wants out to pretty much the edge of the observable universe, when it gets some gravitational lensing involved, it will also be able to see the first stars as they're forming in the universe, which is, again, a huge wish list for astronomers. So, and they'll have to wait for an even bigger telescope to be able to see those first stars anywhere it wants to look. But it's a good next step. So,
worth the money and the wait.
well, $10 billion in 20 years. I don't know. It's astonishing. I'm so glad and everything's gone so great. And I feel like I'm going to wake up from a dream, but would astronomers want this or 5 Hubble Space Telescopes? I don't know. All right.
5 Hubbles would be really nice.
Yeah, I know.
It'd still be oversubscribed. We'd find a way to.
That's exactly it. So that's the part that's tricky. All right, Alex, let's talk about machine learning for exoplanet cartography.
Yeah. All right. So this is a good segue. So with these next generation telescopes, James Webb, but thinking even farther down the line, we're talking about Nancy Roman or HabEx or LUVOIR. Looking farther down the line, we've already done some direct imaging of exoplanets, but we want to do a lot better in terms of going farther out into space. Right now, mostly the directly imaged planets. By the way, we've been doing direct imaging for, I don't know, 10, 15, 20 years now. It's been going on for quite a while. And yet we still only have a handful of these planets, really, that we are able to do this for, because by and large, these systems are very close to us. They are young systems, meaning that we are seeing these planets shining by their own light because they are only a few million years old. They're still retaining their heat from their formation, and they tend to be very far from their host star. So going forward with direct imaging, we're trying to push farther out, get what's called the inner working angle, meaning how close can we get to the star. We want to get that shrunk down so that we can see these planets that are more like Earth, that are in the so-called habitable zone. Get close enough to the star that we can actually see smaller planets, and hopefully not shining by their own light, but shining by reflected light. This is really sort of where we want to see this field going. We're characterizing these planets, and JWST, for example, one thing that we're really interested in is understanding the atmospheres of these planets. But this paper is going a step farther, and we're actually trying to image the surfaces of these planets, or at least figure out what's going on these surfaces. So imaging is maybe not even the right word, but we're trying to map these surfaces. Now, this new paper is not the first people that have tried to do something like this, but they've taken it a step farther, which is pretty awesome. So let's get into the details here. When we are making these direct images of these exoplanets, there's still going to be like a single pixel of light. So how can you possibly get a map of the surface of these planets from a single pixel of light? Well, the big buzzword in astronomy, one of them, is machine learning, right? So we're going for machine learning. Again, everybody wants to check that box and get into the machine learning game, and specifically convolutional neural networks. Now, convolutional neural networks are typically used in things like image recognition, right? So you feed your code, 10,000 images of stop signs, and then you give it a new picture and say, is there a stop sign there? And it says yes or no. Convolutional networks are pretty powerful. I've used them myself. So in this case, they're using convolutional neural networks to try to build a map of these planets. That sounds very hard to do, and it is. But here's what they do. They take these images. What we're going to do is we're going to observe this planet several different times in the course of its orbit, right? So in their case, they want to observe it 8 different times as it goes around, and actually do that 8 different times because the planet, of course, is spinning, right? So you look at it at 8 different points in its orbit, and you sample it several times so that you see different sides of this planet. So what they do in this paper is that they have generated like 4 million model planets, and they've got surfaces covered with oceans and deserts and vegetation and cloud cover. They build these models. They model what they would look like, and then they shrink it all down into a single pixel. Now, even I talk about that it's a single pixel. There's more information than just a single point of light, because one thing that we can do is look at different wavelengths of light, right? So with the integral field spectroscopy, we're looking at 400 nanometers, 500 nanometers, 600 nanometers, 700 nanometers. These planets are going to have different reflectivity, different albedos at these different wavelengths. And if you see it at several different wavelengths, you get color information as well. And not only that, sort of the new thing that they do, I think, in this paper is that they also bring in polarization, right? So light generally is, unpolarized, but if you reflect it off of the surface, you might get linear polarization, or you might even, sometimes even circular polarization. They don't look at the circular polarization here because it's extremely weak, but you can look at linear polarization. So you get polarization information, which they anticipate for future telescopes. We don't get this with JWST, but you get polarization, you get multiple wavelengths, and like I say, you observe this planet at something like 8 different places in its orbit, 8 different times a piece, so that you're seeing different sides. And they throw all of these models in, and it turns out that they can build, reasonably accurate maps of these surfaces with these convolutional neural networks. Now, as you might imagine, it's a signal to noise issue. So if you have beautiful, pristine data, you really can get a fabulous map coming out of the network on the back end. And the lower your signal to noise, these maps look less and less like the real thing. But you can still sort of infer, like we're seeing oceans. They even build in, there's a glint from the oceans. There's a refraction. There's a rainbow. You can see all of this stuff. It all gets built into the model, and it all comes out of the network on the other end.
There's a transit of the exomoon. Right?
Yeah, we would hope. Right. So, yeah, I mean, this is really amazing. You think, we were talking a couple of weeks ago about the solar gravitational lens, right? We're always trying to think about these crazy ways that we can really get fabulous pictures of these surfaces, because it's what we want to see. That is as exciting as that idea is. I think it's, maybe 100 years down the line, if not more, that we'd actually fly out there several hundred AU and try to use the sun as a gravitational lens. So in the near term, how can you possibly get an image of these, or not an image, but a picture of these surfaces? Ordinarily, we're just thinking always in terms of bigger and bigger mirrors, but that's very, very challenging, especially in space. So if we can, do something like this with a single pixel of light and integral field spectroscopy, we've already got it, right? I mean, we can do this. We can look at different wavelengths, and the polarization is something that we know how to do as well. So, this really seems like it has a lot of promise going forward.
I mean, we're never going to get more than 1 pixel, like. Even with a telescope that's 100 meters across, we're never going to get more than 1 pixel. That's all you get. And so you've got to build up a map of this thing. So it's just a number of observations you can make. Is that number of observations a ridiculous amount? Or is that, because that feels like that's not very many. 8 observations of the planet as it goes around the sun.
Yeah, I mean, I don't think it's crazy.
64?
Exactly. 64 observations is what they've modeled. Right. And, your integrations are something like, a few hours time. So there's all kinds of things that they leave out. They leave for future work. This is beyond the scope of the paper is the favorite phrase of astronomers. For example, they have the cloud cover is static, right? So that is going to be confounding. If you actually have variable surface features, that would be sort of challenging. And obviously, Earth has a 24-hour day. If you're integrating over 3 hours, that you're going to see a significant amount of blurring of those of the features during that amount of time. So
maybe that's an advantage too. Like maybe you can feed that into the machine learning algorithm, and it can then take a blur and use that as a way to watch how the brightness changes over some amount of time over your integration, and then that gives you some additional information as well.
That's right. I mean,
we don't have a great way to find the rotational period of a planet yet. So that'd be nice.
Yeah. So actually, that is something that they also do in this paper, is that they can look at not just the rotational period of the planet, but they can actually infer the orientation of the axis of this planet. And so that's, I sort of skipped over that entirely because the cartography is really the sort of the juiciest part of it. But, understanding the axial tilt of this planet is something that would be very valuable. It's something that I've thought about a lot in terms of exomoons. When we think about something like Kepler 1625, where we have a moon solution that has it very much inclined with respect to the orbital plane of the planet. Question has always arisen in my mind. Well, is the planet also tilted over like that? Is it very inclined, kind of like Neptune's largest moon, Triton, or are they sort of co-aligned, the equator and the orbit of the moon? I think that's very important for understanding the formation of these moons. How they came to be, whether it was born out of a disk of material around the planet, or whether it was captured. And so axial tilt information is quite valuable on its own.
Did they say which telescope they want? Like, would this work with Webb? Would this work with the extremely large telescope?
They talked primarily about, they kept mentioning Nancy Roman telescope and HabEx. And in both cases, they're talking specifically about using a star shade. Right. I think that's mostly about getting a good inner working angle, so that you can see a truly Earth-like.
So they want that star shade, yeah. So the HabEx, or even there's been plans for launching a star shade to go with the extremely large telescope, so it would fly above the Earth. And
that's wild.
yeah, it's a crazy idea. That, John Mather, Nobel laureate John Mather, the idea, the brains behind James Webb, this is his next idea.
Wow.
Is launching a star shade to go along with Earth-based observatories. So,
cool.
the idea has a pretty solid underpinning.
Alex,
awesome.
This is cartography, not topography. So it's not the elevation of these features, and more like this part is covered with an ocean, this part is vegetation.
That's right. Yeah. So if we want to do topography, we have to, of course, go back to your famous paper, Exo Mountains.
Famous paper with like 5.
Good plug there.
How many citations?
I haven't written a paper about that.
That well-cited Exo Mountains paper.
Yes.
I was just curious. I wanted to know if I had competition.
Yeah, just cartography. So the topography is still left to you.
Perfect. But you could see the shadows of the mountains different times of the day. I'll bet you they could get it. I'll bet you it's in there.
Yeah, I'm sure there's a way.
Yeah. Interesting. Yep. Very cool. All right. Solar flares.
Yes. There were a lot of news stories about solar flares this week, so I'm smushing a couple of them together. One of them was about solving this 60-year-long mystery about the mechanism behind solar flares. So we know that solar flares happen when interweaving magnetic field lines in the sun snap back to their original configurations, and that releases a lot of energy. The most energetic solar flares, called X-class flares, can produce enough energy to interfere with our electronics. And they happen through a process called fast reconnection. We gave this process a name 60 years ago, but did not know exactly how it happened until now. So the study from NASA's Magnetospheric Multiscale Mission, or MMS mission team, reveals that this process might be due to an actually pretty simple and common phenomenon here on Earth called the Hall effect. So I'll try and give some E&M background here. The sun is made of plasma, so it's a sea of charged particles and free-floating electrons. When charged particles when those charged particles travel perpendicular to the magnetic field lines, then charges get built up on different sides of the field line, and when you have different charges on different sides of the line, you have this voltage difference, which produces an energy vacuum. And then when the lines eventually snap back into place, and this happens pretty quickly on the scale of a couple minutes, that energy vacuum implodes and gets converted into heat and motion. So that's when we get these really strong magnetic flares from the sun. The Hall effect is used in plenty of technology here on Earth, but one of the most interesting uses for it is in nuclear fusion reactors. So if we can better understand this mechanism in stars, then it would help us better control the technology here on Earth. And also, it would help us predict solar flares, which is not as exciting as predicting earthquakes because they aren't as destructive, but it is still pretty important, especially now as we head towards the peak of the solar cycle. The sun is getting more and more active.
I'll bet you a bad solar flare would cause as much devastation as a bad earthquake.
Yeah,
right.
I mean,
when you think
global,
about
right?
our technology and how dependent we are, and so if refrigeration, electrical grid, communication systems, yeah, it could be very bad if a really bad one hits. Like we had one hit Quebec in 1989 and took out a big chunk of the electrical grid in the middle of winter in Canada, in Quebec. And it was very bad. Yeah, I don't think there was many deaths, but you can imagine the wrong like a Carrington event at the wrong time of the year would be rough. So yeah, the better we can learn about these, the better.
And it is getting more common now. The April had a lot of solar magnetic activity, and just yesterday, NASA's Solar Dynamics Observatory detected one of these really strong X-class flares coming from the sun, from a newly formed sunspot that doesn't have a name yet because it is so new. But lucky for us, the flare was not directed at us. It was on the other limb of the sun, so it didn't hit us, but one could be coming.
Yeah. So there was a really interesting post on Twitter I read, and it was a researcher working with ion engines, with Hall effect thruster engines, and he was saying like the most spacecraft ever use Hall effect thrusters right now. You think about all the Starlinks, they're all using Hall effect thrusters. So right? So they're all using ion engines. And the crazy part is that scientists don't entirely know how they work. That they use them and it works, but they don't understand why deeply. And you're like, well, of course they do, because so I read this post and he was like, yeah, the most common rocket engine in the world, scientists don't know how it works. I'm like, what's this clickbait nonsense? And then the guy explained exactly what he was talking about, and you're like, oh wow, okay, yeah, that's crazy. That we don't this concept, this Hall effect, is actually really tricky and has puzzled physicists for as long as when it was discovered, and they still don't understand all of the pieces to bring together. And so to see it both tested in the lab, but also to see it on the sun and to be able to bring these concepts together is kind of amazing.
Yeah, it is really cool to know that something that happens in the sun is something that we've been taking advantage of for a long time here on Earth.
Yeah, really cool. All right, so we got an announcement this week from the European Southern Observatory, and they said that on May 12th, they're going to make an announcement, and it's going to be a public announcement Thursday, May 12th. So what is that? It's about a week, a little over a week from now. What's it going to be about? It's very rare that the European Southern Observatory puts up a great big announcement of some event. So here's all the pieces in play, and see if you guys can work this out. See if you can imagine. So again, an analogy that I saw on Twitter was, imagine someone hands you a present, and it's a nicely wrapped present with a wagging tail. What could this present be? So the announcement is coming from the people working with the Event Horizon Telescope, and it is an exciting announcement about the Milky Way. What could it be? What could it be? Yeah. So, of course, about like 4 years ago, the people working with the Event Horizon Telescope took images of two things. They took an image of the supermassive black hole at the heart of the Milky Way, Sag A star, and they took an image of the heart of galaxy M87, the supermassive black hole. Then it took them about 2 years. They had to fly hard drives back from Antarctica at the right time of the year. They had to bring all of this data back together and crunch it for years. And then we finally got this announcement of M87. We got the picture, the first ever picture of the supermassive black hole, its event horizon at M87. And everybody was really surprised because, like, why did we see M87, but we didn't see Sag A star, which is closer? You would think that's the one. And luckily, the two objects are visually about the same size in the sky. It's just that Sag A star is very close, but relatively smaller. M87 is gigantic and farther. And so when we were covering this, I kept asking this question, like, why did we see the far one first? And the answer is that the environment around M87 is gigantic. And so the motion of material swirling around the supermassive black hole is relatively slower from our perspective to the one that's coming around Sag A star. It's a very dynamic environment that was very difficult to do all of the mathematics and all of the calculations to be able to tease that number out. And so they had to keep working. They were able to get one picture out, but they weren't able to get the other picture out until now, I think. So what is this this present with the wagging tail? It is probably going to be the image of the supermassive black hole at the heart of the Milky Way, Sag A star.
Super exciting.
To see it.
Yeah, we've got a lot of people working on this Event Horizon Telescope here in Taiwan, so it's something that people are very excited about around here. I've been out of the office for several weeks with COVID, so I haven't really gotten the word on the street from folks, but I think that's, it's going to be a very exciting time. I think if memory serves, I can't say who I might have heard this from, but, they've got observers and they've got theorists. And the theorists, my understanding is that the theorists always really want to understand everything that they're seeing, and the observers are kind of like, well, we see what we see, and let's get it out there, and the theorists can figure it out later. So I think in some cases, not to throw any shade at the theorists, but it's a huge collaboration, and they've got to bring all of these pieces out all at once. And so, as you say, this imaging has been going on for years now, and so you sort of those of us who can paw at our beards will paw at our beards and wonder what's going on here, what's taking so long. And it's because they've got to wrangle literally hundreds, if not thousands, of scientists together to bring all of this all this out to the public all at once. The observations as well as the interpretation of what's going on.
Yeah, I'm really excited for the interpretation because the pictures are beautiful, but the thing about the M87 image that really excited me was when they started to learn more about the way magnetic field lines rotate around black holes, and I'm curious to see what the potential Sag A star picture would tell us.
So the observing run was done back in 2017.
Wow.
So that's when they did the first observing run with the event, and then they crunched the data for 2 years, and in 2019, that's when we got M87, and now here we are 3 years after that. So it's been 5 years since the picture was taken, and it was like 2 weeks, I think. Like, it was just a couple of weeks that they actually gathered the data for that observing run. And astronomers have been crunching these numbers ever since. The picture you're looking at right now, this is actually the updated version of the M87. You can see these swirly little lines in it, and that comes from the polarization around M87. So they were able to tease out further polarization information that helped further secure just that the observations of this event horizon matched the predictions made by the theorists. And so you're literally seeing the polarization of the matter as it's being swirled around the event horizon of this supermassive black hole. It's hard to wrap your head around how big this is.
I'm really can't wait to see this image. I wonder how different it's going to look from M87, or if it will look the same, and what the public reaction will be to this image. If it looks identical to the M87, and I really don't know. I'm obviously out of my element. I wonder what people will say. The first time we saw this, it went around the world. People went nuts for this image for a good reason. It's really, I think, one of the most seen astronomical images that there is, even, just a few years old. But at the time, it really ricocheted around the world. It was on newspaper headlines all over the world. It'll be very interesting to see what the reaction will be this time around. If it's kind of like, oh, yeah, well, we've kind of seen that before. Obviously, I'm super excited about it to see what's going on in the Milky Way. Sagittarius star is super fascinating. M87, as cool as it is it feels a lot more remote to us. So I'm super excited, but it'll be interesting to see what the reaction will be.
My guess is that it's going to be worse. That's my feeling, is that it's going to be worse because it's a more dynamic, a more difficult image to take. And it's not like they've been sitting out there year after year building up a better and better image and refining their data and working with it. They have been crunching this data for 5 years, and it's the data they took on the same time that they took M87. So my guess is it's going to, and this is just my guess, like, please, who knows what it's going to look like, but my guess is it's going to be like a little blurrier, a little fuzzier. It's going to reveal a lot of the same kinds of information that they're hoping to find out. It's going to match the predictions, but it's not going to be as pretty as M87. And unfortunately, that's pretty much it. You get M87 and you get Sagittarius star, and there's like one other black hole that's big enough and close enough that we could try to see the event horizon. You're gonna need a space-based observatory, something on the moon, to increase the resolution to start bringing in more. Like if you add a satellite at, say, geosynchronous orbit height, you can then take pictures of dozens of supermassive black holes, because you're creating an interferometer that is vastly bigger than the Earth. But the Earth just isn't. You can't make the Earth any bigger to take a bigger picture.
It makes me sort of think. I wonder why we can't, or maybe people have thought about this. I'm clearly out of my element. That should just be the caveat on everything that comes out of my mouth during this segment. But you would think that maybe one thing that we could do, not image any more of these supermassive black holes, because they're not that many available to us. But looking at sort of these black hole binaries, where the black hole is accreting material from a companion star. Those are clearly much closer, much smaller. These are stellar mass black holes, but there's certainly a lot more of these things and a little closer to home. So I wonder if anyone is thinking about
right. But you've got say you've got, let's say, Cygnus X1. You've got a black hole that is 10 times the mass of the sun, and it's 5,000 light years away. But if you go 22,000 light years away, you have one that is 4.1 million times the mass of the sun. So, so no, supermassive black holes just are overwhelmingly bigger and more massive than the stellar mass black holes. You can definitely pick up a lot of stuff from the stellar mass, but it just doesn't compare to the months. Again, like M87, I forget how far away M87 is, but it is in the dozens of millions of light years away. And yet it's gigantic.
It's huge.
Yeah.
Right.
Yeah, the resolution. So who knows what's going to happen? You'll find out with, I have no advanced information. No one has offered to give me any embargoed information. I'm guessing like the rest of you, and
it should be coming soon, right?
But it will be very soon, and I'm saying just like prepare yourself emotionally.
I mean, as far as press is concerned, if it's coming out on the 12th, then maybe there's some sort of advanced, sneak peek for folks in the press.
I would assume so. Well, so we don't look at embargoed material at Universe Today. And at this point, I think everyone knows to steer clear of us. So none of us know at Universe Today, which is just how we like it. But we will find out together on the release day. All right. Well, we've reached the end of our show. We did it. No guest.
Wow, we did it.
Shorthanded, and yet we brought you some news. So I hope you were all. Are you not entertained? Alex, tell us what you're working on and where people can find out more.
Working on exomoons. All the time. And I'm gearing up for the summer. I've got a couple students coming in to work with me for some exomoon projects. So I'm very excited about this. And if people want to follow me, they can follow me on Twitter is the best place, @AlexTeachy.
Moya.
You can also follow me on Twitter @GoAstroMo because Moya McTeer is harder to spell. You can find my podcast, Exolore, EXOLORE, and you can pre-order my book about the Milky Way, which I know already has something wrong in it because of this embargoed thing coming out. So that's great. But it's called The Milky Way, an autobiography of our galaxy, and you can pre-order
You don't
it now.
know. They could literally just be a press release that says that everything Dr. McTeer said was exactly right.
Here's hoping.
Here's hoping. All right. Well, I'm Universe Today on all the things. Today I had a fascinating interview with Dr. Sam Howell from NASA JPL, and we talked about exploring under the ice on Europa, and he's part of the Europa Clipper team. And so we talked about just these ice worlds and talked about what Europa Clipper is going to find. But then we spent a good hour figuring out practically how one sends a cryobot through the ice down to the subsurface ocean on Europa and tries to explore it. It was a fascinating conversation, and I really reached the end of all the questions that I had about it. So if this concept if you want to learn about European space whales, this is the interview that you're going to want to definitely check out. All right. Well, thank you. Thank you, Moya, Alex, for joining me today. Thank you, Pamela, for engineering behind the scenes. Thanks, everyone watching us on YouTube and on Twitch. Thanks to Nancy and the rest of the moderators for keeping everything organized. We couldn't do this without you. And we will see all of you next week. Thanks, everyone.